So now, I would like to invite Jan to slam as our first slammer. Poor guy. So how can I present you? Jan! Oh, the professional one. Like 1, 2, 1, 2.
Can you hear me?
Oh. I have something incredibly nice to say about Jan. Like, it's annoying to me because you're against my friend Adyasha. Like, so I don't want to be nice with you, but you're awesome. Because Jan just told me that he has prepared everything in German. And it's true, like he did prepare everything in German. But as there's so many English speakers here, he will present in English. So for this, honestly, Jan, a big applause.
Enjoy.
You enjoy life? Yeah. Oh, whoa, he's fast and responsive. How many side slams have you done already?
6, I guess.
Uh-huh. Okay, 6 side slams. Well then, I let you do. I count down to 1, and at 1 you start, and the counter counts. Do you have anything more to add? Any questions? Do you want to? No, you're fine. Okay, so 3. Ah yeah, sorry. Oh, awesome. The pointer, yeah, the pointer is also an important instrument. 3, 2, 1, 0, go Jan.
Good in Zürich. No, nobody hears me? Okay. So, there's everything missing actually. Okay, then I need to improvise because the slides are not correct, sort of. So my topic is biodiversity. And in particular, I would like to understand why marine biodiversity, like in the oceans, and biodiversity on land are so different. And biodiversity, let's say, is just like an observable, just like the sum of all species. But today I would like not to focus on the number of species of the biodiversity of today, or of yesterday, or of last week. So my topic is like a couple of million years ago. So why is the biodiversity in the oceans different from continental? And the question is, how you count the species actually, because many of those species went extinct, and so like 100 million years ago the world was different. So and the answer is that you have just to dig. You dig, and if you dig deep enough, then you find some fossils actually. And then you can count the number of species. And people did this. And this blue curve, now this is the scientific part, is the biodiversity, the number of families or number of species. It's more or less proportional. So you have in the beginning some growth. Then you have a sort of stagnation. And 200 million years ago from today, there's like an exponential growth in the oceans. In contrast, the continental biodiversity started a little bit later off, so life originated in the oceans, but it was always more or less growing. And open question is, why is that? Why it's different? Why you have stagnation phases of 200 million years in between in the history of the Earth, in the ocean, but more or less not so much stagnation in land. And for this we created a mathematical model. And it's actually quite simple. So it's a network model, and some species are sort of dependent on each other. Meaning you have maybe a bee, and the bee needs a plant to eat, to forage. And also some plants need bees to whatever it is, to reproduce. So, and this is this purple stuff. So the problem is, so some species are so dependent of each other that they build sort of trees, and meaning if one species go extinct, then this means that the whole tree goes extinct. That means many species die out. On the contrary, our model tells you the following, that like at random, there are speciation, meaning new species will, so new species are created. This is the model, and at random some species die. And this tree you see, this networks, this interconnection, this dependency of many species of each other are sort of random. So our model has like one big ingredient, this is like randomness, and the other one you have the domino effect, which is like cascading extinction of species. And this is it. So, and this was maybe a little bit too fast. So in order to really to understand something, you have to do it. So now it's on you. So now I suggest the following. We do something like this. But the good thing about it, you have to stay where you are. I mean, you cannot move. Even if I told you, you would not be able to move anyway. So, and now we have this event of randomness, okay? So the randomness is that we have now speciation, which is always green, Artenentstehung. And so you have a first name, right? What is your first name? Louder. Andreas. Andreas. So, applause for Andreas. Andreas, what is the first letter of your first name? A, right. So, and now I want you the following. You should remember your first name and the first letter. Okay? And now you are a species. Each of you are a species, okay? So I'm meaning, so if I give you this sign, you should shout out the first letter of your first name. This is your species. It could be a cat, but usually if your name is Zander, then you call Z or Z. Okay? So this means you speciate, you come to life. But you may be dependent on somebody else. And now, after you shout out something, you grab somebody's shoulder. And you can also grab some other parts of the body. It's really on you, but it depends on the neighbor. Be cautious. So you can, I mean, okay, you know what you do. So you grab the shoulders of the partners, meaning, and then your partner will be dependent on you. Meaning, if for some other reason he will take his hands away from your shoulder, you will die. Okay? So, but first there's no extinction here, no death. So now please all people from L to Z, please shout and select one partner now. Everybody. Okay, so I don't see any change, but don't worry, and keep it. So in particular, not only the couples here, I mean this is not, we need to have like really a biodiversity here, okay? So both hands stay, but stay where you are. So now comes another random event. This is my model. So extinction. So now everybody from A to K, wait for my sign, go extinct. This means if you go extinct, you take away your hands from your partner and you shout out just like X for extinct. So now A till K now. Okay, so now I would also hear people whose first name is not from A to K, because you went extinct, because somebody killed, somebody took the well in their hands, okay? So, but we will learn. Okay, next random event, and stay calm. So now, from L to Z, you will be created. Shout your first letter. And take some neighbor and keep it. Okay? I don't see anything here, but anyway. Okay, so now next random event. So L to Z go extinct now. Okay, so now I want to have avalanches. So it must be avalanches by construction because it's not so random. So it's, take care. So from A to K, now you speciate. You... Okay. I guess we skipped this a little bit. Also some fun, I'm sorry. So now everybody got extinct. A to Z. Now. Okay, what we have learned. I guess you really see, so all these avalanches going like through the whole biodiversity of Earth, you go extinct, some species speciate and so on, and you now understand exactly what I meant, right? So, but what does the model tell us? So this is a line also a couple of 500 million years back into the past actually. And for example, 65 million years there was like a big event, a big asteroid came to Earth, and as a consequence there's a peak in extinction here. So many species died, many families, like 20-30% or something. But you see there's always a constant background extinction. Meaning, so to explain the biodiversity of the Earth, we actually do not need this big 5 events or five events like big volcanoes and so on. Right? So this is what the model tells. And what you can see from the model is, if you combine some parameters from the fossil record, from this catalog, from this database of the fossils, then you can see why the marine biodiversity has some sort of stagnation sometimes, in contrast to the continental biodiversity, where it's like always growing. But it's a little bit more complicated to see. But the reason is because 1-2 parameters which you can infer from the data does this. And the question is, for what is that good? It's also good for today and tomorrow's biodiversity, because if we understand how the avalanches of extinction work, what is the minimal model, we can also maybe protect our species on Earth. And we humans are quite good in killing them. Thank you very much.